Topic number 8 on magnetic flux, inductance, and Faraday's law. The learning outcome. So at the end of these topics, we expect you to able to calculate magnetic flux through a plane area or circuits due to both uniform and non-uniform magnetic flux density B. Able to find the self-inductance L of simple circuits, understand the meaning of mutual inductance, and then apply Faraday's law on electromagnetic induction to find the induced voltage across some simple circuits. Okay, magnetic flux. So we have studied electric flux in electrostatics. So this is the equivalence. So first we consider a uniform magnetic flux density B. Since B is called the magnetic flux density, then the magnetic flux will be the flux trading through a plane. The magnetic flux is equals to B times the surface area of the plane. And the equation is valid only if B is perpendicular to the surface concerned. So this is similar to the electric flux that we have studied. So if we have a plane here, we define a vector surface area that is perpendicular to the plane. And if B is at an angle with the surface area vector, then we write down that the flux will be equals to B dot S equals to B times S times cosine theta. Generally, the magnetic flux will be equal to the surface integral of B dot ds for non-uniform magnetic flux density. For uniform, it's simply just multiplied by the surface area. For non-uniform, so you have to divide up the area into infinitesimally small area called ds. So here, and then B dot ds, and then integrate it over the whole area. Okay, so meaning that I have many of this. Just integrating means that you sum them all up of all the contributions. The SI units of magnetic flux is in Weber or is Tesla meter squared. And again, it's a scalar, so it's not a vector. So it's also a scalar, just like your electric flux. So an example, find the total magnetic flux density trading a plane circular area of radius 1 centimeter when it is subjected to a uniform magnetic flux density of 1 millitesla applied A in the plane of the area, B perpendicular to the area, and then C at an angle of 50 degrees to the area surface normal. So first one, what is the flux? 0. Second one? B times S. S is equals to pi r squared. R is 1. So there's pi centimeter squared. And then times your 1 mini Tesla. And then this one will be okay, so solution. So obviously the first one is 0 because it's not cutting through, the flux is not cutting through the plane. The second one is just the magnitude of the 2 multiplied. So B times pi r squared. So 3.14 is pi, yep. Pi times 10 to the power of minus 7 Weber. And then the third one will be multiplied by a cosine 50 degree. And they give you 2.02 times 10 to the power of minus 7 Weber. Okay, so that is the magnetic flux. Inductance, self-inductance. So consider a circuit carrying a current I, as shown in the diagram. So the current, you have a current flowing. So this current will generate magnetic flux density B in the region surrounding the circuits. And then consequently, there will be some magnetic flux phi cutting the plane of the circuits. You have a current, the current generates magnetic flux density, and that magnetic flux cutting through that plane of circuits. Okay, so that is called a self self-inductance. We define self-inductance of the circuits to be the magnetic flux divided by the currents. L is equals to phi, capital Phi, divided by I. And we know that the SI unit of inductance is in Henry, or equivalent to Weber per ampere. Okay, our flux is in Weber, current is in ampere. Weber per ampere is our unit Henry. Again, L is a scalar quantity and it depends on the geometry of the circuits. If a core has n turns and each turn has a flux of small letter phi here, then the total flux cutting the coil will be a capital Phi equals to n times small phi. And this is called the flux linkage. So one coil gives you flux of small letter phi, and then the flux linkage will be n phi. Okay, so we're now going to look at some structure and calculate their inductance. Long solenoids. So just now in our previous topic, we have worked out the magnetic flux density of a solenoid. Inside that solenoid is equals to mu naught n times I over L. L is the length of the solenoids. Okay, so we have a current. The currents generate magnetic flux density B, and then this magnetic flux is cutting through the plane of our solenoids, and therefore we can work out what is our flux. So our flux, it will be B times A, which is mu naught n times I times A over L, and then our solenoids has n times of coil, so the flux linkage will be n times this phi here, and we end up with mu naught n squared I times A over L. And then divide this by the currents that give you the self-inductance. Okay, so the self-inductance will be mu naught n squared times A over L. And just now I said that we can use a small letter n to represent number of turns per unit length, which is the capital N over L. And if you substitute back to our equation 3a, we find out that the self-inductance is approximately equals to mu naught n squared times A times L. Okay, so that is the self-inductance of a long solenoid. Okay, so self-inductance, the inductance generated, or the flux is generated by its own current and then cutting its own circuit. So find the self-inductance of a long circular solenoid of a length 3 centimeters, radius 3 millimeters, number of turns is 3000 per meter. And what is the self-inductance per unit length? L equals to 3 centimeter. R is 3 millimeter. And then small letter n is 3000 turn per unit length. And then you're asked to find what is L. Okay, so back to our equation here. L equals to mu naught n squared A times L. So here you can find out what is A. Length is given. Okay, so the self-inductance is 9.6 microhenry. So this is A, L, n squared. And then per unit length is simply divide by L. That gives you 0.32 millihenry per meter. That's how you work out self-inductance. Back to our parallel plate transmission lines. Okay, we have calculated the magnetic flux just now. Okay, that magnetic flux that we derived just now is B equals to mu naught I over A from Ampere's law. And then the magnetic flux outside the plate is approximately 0. And then the flux linkage phi is equals to, so our magnetic flux is over this, cutting through this plane, which is this plane. Okay, so our magnetic flux is in these directions, and therefore it will cut through this plane. And the area of this plane is L times W. Okay, I use S which is that will be W times L. Okay, so that will be this area. No, it's L times D, correct? Not W, it's L times D, which is this area A, B, C, D. Okay, so DC is L, BC is D. This separation here is D, therefore this area is L times D. Okay, so my flux linkage will be my magnetic flux density B times that area S, which is L times D. And then the inductance, self-inductance will be phi over I, that will be mu naught D times L over W. And that will be the self-inductance of our parallel plate transmission line. And then per unit length, we simply divide by the length L, and that will be mu naught D over W for our parallel plate transmission line. Coaxial cable. So our magnetic flux density is mu naught I over 2 pi R. And then our coaxial cable looks something like this. And then the magnetic flux is going around. Okay, so the area that is cutting is in this area. Okay, so going around that coaxial space between them. Okay, so this will be my A, B, C, C, D, which is my area here. Okay, so here, our area, this area here, so because the flux in this case is not uniform, so it changes as we go further from the center conductors. Okay, so it's mu naught I over 2 pi R, it depends on R. And therefore, we have to do integrations. So our flux will be, integrate this over the space, which is from A to B. So we're doing mu naught I times L over 2 pi, and then dr over R, integrate from A to B. Unlike in the previous example here, or this example, we just simply multiply by the area, because in this case here, we said that the flux is approximately uniform across this space here. Okay, so therefore we just multiply, we can take B times S equals to the flux. Whereas in this case here, the flux is not uniform across this space. It's higher, the flux is stronger here, and then if you go further out, the magnetic flux density decreases with distance. And therefore we have to do an integration here. So our flux linkage here is mu naught I times L over 2 pi, integrate from A to B dr over R. Okay, so integral of R dr, that will be natural log R, and then we have a limits A to B, that will be over limits A to B. And therefore we end up with mu naught I times L over 2 pi natural log B over A. And then the self-inductance will be the flux linkage divided by the current, and then that get out with mu naught L over 2 pi natural log B over A. Per unit length divided by the L, which is the length, and that will be mu naught over 2 pi natural log B over A. Okay, so this is self-inductance for coaxial cable. Okay, example, coaxial cable has an inner and outer radius of 1 millimeters and 3 millimeters respectively. What is the inductance per unit length? Just direct application of the equation 6b. Inductance per unit length equals to mu naught over 2 pi natural log B over A. So this is B, this is A, our coaxial. Okay, so we simply apply that equation 6b, can work out the self-inductance, which is equals to 0.22 microhenry. Okay, so remember when we talk about the long wire, in the case of coaxial, we have the core or the inner conductors. There's also magnetic flux in that wire. So for radius r smaller than a, there's also magnetic flux inside that center conductors, and therefore there is also contributions of self-inductance, and that gives rise to an additional mu naught over 8 pi, and then the total inductance of our coaxial cable is mu naught over 2 pi natural log b over a plus 1 over 4, which is, so this comes from the inner conductor per unit length. Okay, so this is for low frequency. Because at low frequency, the current is uniformly distributed across the surface of the inner conductor. At high frequency, this is no longer there, because at high frequency, the current is actually just on the surface of the conductor. Okay, so the current is mostly at the surface of the conductors. Okay, high frequency is simply equals to mu naught over 2 pi ln b over a, because current flows on the surface of the inner conductor. Okay, so that is the inductance for coaxial cable. Okay, so here's it. At very high frequency, this flow in a very thin layers or at the surface of the inner conductors. So therefore, the magnetic flux density is approximately 0 at inside the center conductor. So we have self-inductance just now, and now we have mutual inductance. So self-inductance is from its own circuits. Mutual inductance is from an external circuit. Suppose we have a circuit carry a current I, and it plays in the neighborhood of a second circuit. So this is a circuit. Circuit 1 has a current. Circuit 1 generates magnetic flux, and that magnetic flux cut through a second circuit. Okay, and then this flux gives rise to some inductance in this second circuit, and that is called the mutual inductance. So second circuit doesn't carry any current. The current is in circuit 1. Circuit 1 current generate magnetic flux, and therefore that magnetic flux cut through the second circuit that gives rise to an inductance. Okay, so the mutual inductance is defined as phi 2, the flux linkage at the circuits 2, divided by the current in circuit 1. Okay, so you can see that you have phi 2, I1, and then the subscript is called M21. So the first subscript refers to the flux linkage. The second subscript is the current. M12, you can see that M refers to the flux linkage at circuit 1, and then 2 refers to current at circuits 2. Okay, so it's important the order of the subscripts that tells you who is generating the currents for the flux. Okay, so in this case here, circuit 1 has the currents that generate the flux, and the flux is cutting at the circuits 2. Here is the circuits 2 that has the currents flowing that create the flux, and that flux cuts circuit 1. For energy considerations, it can be shown that M21 is actually equals to M12. And therefore, we can simply write M referring to the same as M21 and M12. And the mutual inductance has the same units as self-inductance, is also measured in Henry.